For example, in the resource theory of, say, purity, then if you can imagine two versions. One where you are allowed to add maximally mixed states and do unitary transformations and trace out things. In that case, majorization becomes the set of majorization conditions become the unique set of monotones. So you have a whole bunch of second laws provided by majorization is the language we would use. If I consider catalytic processes, in other words, I'm allowed to borrow some state, and as long as I give it back, then the Renyi entropies provide the constraints. So in some sense, you can do more if you have a catalyst, so they're a weaker set of constraints than majorization. Okay. So more generally, you have, for example, these Renyi divergences, which are defined as 1 over alpha minus 1 log of trace of rho to the alpha sigma of, sorry, their distance. Okay. So for the people that wanted to get to the black holes, these will give a new set of constraints for black holes. And in the case of the CFT, so we are able to compute these things by looking at some kind of path integral, some quench, effectively.
When rho and sigma, which one is the black hole?
Well, okay, so this is in the commuting case in some sense, so you can always just trade 1 minus alpha for alpha. In the commuting case, they're equivalent. If they're non-commuting, then you need to there's other definitions of the quantum Renyi divergence. There's like a sandwich one where I take, rho to the, I don't know, there's some, you can kind of put a rho on both sides and a square root and etc. So so you need to be careful when they don't commute.
Well, like it's an initial and final state of the black hole.
That's right, yeah. So you can think of, usually this will be, often we will pick this to be the thermal state, and then you can think of it as a distance. So if here's your state space, here's the thermal state, which in our case would be some black hole at equilibrium. And now you have some out of equilibrium system, and what these Renyi divergences tell you is that you have to get closer to the thermal state, but there are many ways you can get close. There's many distance measures you could choose, and they all have to go down. So
they're all typically actually not really distances because they're not symmetric.
But they're distances, and the important thing is that they have to be, they go down under completely positive trace preserving maps. That's the important thing. Which is, you can think of any measure of distinguishability. So if I have a measure of distinguishability, like d alpha, but this is what I'm going to say is true of any measure of distinguishability. So let me just use d to represent an arbitrary measure of distinguishability. Then it needs to be true. Any measure of distinguishability, almost by definition, should satisfy this property. Right? Because you imagine someone gives you rho or sigma, you're trying to distinguish them, so you perform some CP map on them, and you can only ruin things. You can only make things worse, because distinguishing, you're allowed to do the optimal way to distinguish them. So if you do any other CP-TP map, you only make things worse. So a measure of distinguishability has to go down almost by definition, under any completely positive trace preserving map. So now you see that this thing here also has to be, that this is less than this thing. So E rho is less than this thing. And if this is, so if we, for example, let's pick this state to be in our set S, the one that minimizes this quantity. So this thing here is E rho, okay? Sorry, and this was. So we see that if we have any contractive distance measure, and we take the infimum of that distance measure between our state of interest and some state from our set of free states, then we get a monotone, we get a second law. Okay, and all we've used is the fact that the map is contractive, and that the class of operations preserves the set of free states. In other words, if I start with a separable state, then under LOCC, I cannot get out of that set of states. Right? So all we've used is contractility of this map, and that if I have some set, the set of free states, like the thermal state or the separable states or whatever in my resource theory, then under the class of operations, if I'm in that set, I can never get out of that set. Okay? And I'll just say that we always used to call it the free set, because you can add them for free and not change, and the resource theory stays the same. That is no longer true when you go to multiple resource theories, and so we now call that the fixed set.
Sorry, and this free set is always just a function of the free operations, or is there some kind of ambiguity, like you have to choose extra stuff?
So it could be. So there was a nice kind of extension of our theorem due to, like a beautiful one due to Brandau and Gour, where they basically said, so we, I think, initially defined the resource theory as you have some class of operations, and then you have this set which either could be, you could either choose a class of operations and that would give you the set because it was the class of states you could prepare under that class of operations, or you could just throw in an extra class, an extra set of operation, which is here's some set and you're allowed to add them for free. That's how we thought of it. They, I think, have a different formulation, which is, in my view, a little more elegant, but maybe where they say, okay, let's just choose the set S and then choose all the set of maps which preserve that set, which then in some sense automatically gives you reversibility. So it's a very elegant, it has a nice elegance to it, but it's not as general. So for example, LOCC, the separable states are the ones which are preserved under LOCC. There's a bigger class of operations, separable preserving maps, which are not very physical, but you get reversibility. So it's a nice way to, sometimes you get some nice theorems, but you also, maybe it's not as physically motivated sometimes, but it's nice. Okay, any questions about that? Okay, so that's resource theories. We have many second laws given by, for example, all these Renyi divergences, and we can apply it to thermodynamics and get a whole class of second laws. For example, so here it would be the Renyi divergence to the Gibbs state would provide you with many second laws, and D1 or E1 in this case is just the change in free energy. It corresponds to the change in free energy, the ordinary second law, but you get all these additional ones. In the thermodynamic limit and in equilibrium, they all happen to be equivalent, approximately at least. But for out of equilibrium systems, or when you don't take the thermodynamic limit, they're all distinct. So you get a
thermodynamic limit means infinite number of systems.
Yes. Yeah. Well,
it has almost nothing to do with thermodynamics.
No. Right. So
that's
good.
Jargon from.
No. It's bad jargon from our community. So I guess what I think has not been rigorously proved is that if I have an interacting system and I take the real thermodynamic limit being infinite volume, that I somehow recover, that if I look at these Renyi divergences, I will recover the free energy. It's almost certainly true. You can do it in many cases, but a kind of a very general theorem I don't think has been proven. A physics theorem where you say I have an interacting system. It has to be. You probably need an assumption like the energy should scale roughly like the volume and only have a subleading term which scales like the area, something like this. You probably need some assumptions like this. So if you need some extensivity assumptions, and then you would recover the free energy for physics. At the moment we have it like a string theory theorem. So it's a conjecture. But almost.
There's a button.
Oh yeah. I like this thing. Okay, so first law. Let's give it. Okay, so I want to think of thermodynamics now as two resource theories. I guess like driving a car or something. I need some insurance. We can. I'm glad that it was just that was written there and not something.
Oh, you can try to see what's in these in the middle of the point.
Yeah. It'll be a mystery. I'll leave it as some suspense for the talk. So let's now think of thermodynamics as a double resource theory. Okay, so it's the resource theory of purity and energy. It's one way to think of it. So let's think of the resource theory of energy, which is that I'm allowed the ground state and nothing else, and then everything that has energy is a resourceful state, and the ground states are not very resourceful. So that's the resource theory of energy. You can construct such a thing, and the relative entropy distance to the ground state is a measure of like average energy, basically. Okay. And so that's the resource theory of energy.
And the Hamiltonian here is fixed domains.
Yeah. Yeah. You can consider variations where you can change the Hamiltonian, but then you have to count the change in energy, etc. So that's energy. Then I have the resource theory of, so that's energy. Then I have the resource theory of purity. So the resource theory of purity, my free state, so we call this noisy operations. I'm allowed the maximally mixed state. I can do any unitary and I can trace out, and that's it, okay? So that's like thermodynamics for children in some sense. So you find that the relative entropy distance, so the average energy is the relative entropy distance. So that's the monotone. Here the monotone is log D minus S, the entropy, the von Neumann entropy. So these are two nice resource theories where you see that the relative entropy distance to the set of free states, so these are the free states here, give you, you have the free states, you have the relative entropy distance, which gives you a monotone, and that's an example of a double resource theory that we're familiar with.
Sorry, I'm a bit confused. Somehow you say you can add the ground state, right? This is also means that you're adding a system, right?
Okay, yeah, so in what we've, I don't know. Okay, sorry, go on.
Yeah, so you add the ground state, I guess.
Yes.
You mean you can tensor product the ground state?
Yes,
That means you're adding a system.
yes.
So what's the rule of going from the previous Hamiltonian to the Hamiltonian of the new composite system?
Yeah, so I guess you add, in this case, we'd just be adding the Hamiltonians together. Yeah. I have to admit, it's been a while since I've thought about this, so I'm not sure I remember in full, kind of, the full details. This is, so we did this with, we looked at these things with, originally with a student of mine, Carlos Baracchiari, and Tobias Fritz, and then the second law, this generalized first law, is with Carlo and Lydia Del Rio, just to, and we haven't published it yet, but I can give a draft to anyone. Okay. Okay, so so notice here you have the free states are the ground state and the maximally mixed state. Now, what is thermodynamics? It has a different free state. It's the Gibbs state that I'm allowed for free. So I now construct a new theory, which is the double resource theory of energy and entropy, and it's I am allowed now the Gibbs state, so I'm given some Gibbs state. So this is the double one. I'm given the Gibbs state. And I guess, you know, all of Charlie's stuff with Maxwell's Demon and Landau-Erasure is a very nice example of what the thermal state lets you do, which is, so Carter likes to call this the bank state for general resource theories. I don't like that term. I'd like a better term, so maybe.
Yeah, I don't usually get stuff for free from a bank.
Good. And I just don't like banks, so I don't want to like. Yeah. Maybe it's like it's the reservoir state. So what it allows you to do is convert one. It's an exchange rate. It gives you an exchange rate for converting one resource to another resource. Okay. So so you can think of it like you get it for free, and it provides a way. You can't from the reservoir. You cannot extract both energy and purity, but you can trade off one for the other. So I could invest in some purity and get some energy, or invest energy and get purity. So it provides an exchange rate given by the temperature. It provides an exchange rate or all the chemical potentials, etc., for more general thermal states. It provides an exchange rate for exchanging entropy and energy. So, you know, when we think of a Maxwell's demon, what is a Maxwell demon doing? It has a pure state, so it has some purity. It's putting it in contact with the heat bath, and it's extracting work. So it's converting purity to energy, okay? And what's the exchange rate? It's kT, right? That's the exchange rate because it extracts kT log 2 units of energy. Okay, so the temperature is the exchange rate. Likewise, Landau-Erasure, you have work, so you have some energy and you want to convert it to purity, so you invest some energy and you get from that some purity, and again your exchange rate is kT log 2. If you have a generalized Gibbs state, so you have e to the minus beta h, say minus mu n or whatever, then some people put the beta here, then you can think that you have another resource which is particles, and you want to maybe